What's going on, everyone? My name is Johnny Bandon, and I'm your CCNA instructor for this CCNA video series. So in this video, we're just going to add on to our static routing configuration and really just end the static route section by going over kind of the advanced stuff. So the things that the CCNA wants you to know about when it comes to static routing. So with static routing, we know we have different types, right? So we have floating static routes, default static routes, and host routes that we're going to need to know about. So in this lab, that's what we're going to configure. So if you take a look at our diagram here, before getting into the instructions and going through my typical spiel of this lab's available for you if you're a paid customer, we have our GitLab repo of all the baseline configs and solutions, instructions, yada, yada. Let's just look at what we got here, right? So we have one central focal point here, our HQ router. This would be something like a hub, right? So this is our hub router. And you can see the hub has all these spokes. So it has spoke 1 here and spoke 2 here, which are connected to the same network. So you're going to see configuration in these routers called HSRP. Don't worry about it, right? If you're downloading these labs. And that's how we can get one LAN to use 2 of these routers, right? We have an active and standby. Anyways, that's beyond the scope. So what we're going to do from this HQ is we're going to have 2 static routes going to this destination network. And we're going to see how static routes load balance. And then you see here we have another spoke that has a multi-homed connection. So it has 2 connections down to R2. So instead of load balancing here, we're going to pick one as the primary and one as our secondary. Secondary being our floating static route. So that floating static route is going to be another like wicket we hit, right? And then also in our instructions, we're going to have a host route built using that secondary route there. And then we have our ISP up here, and this is going to be where our default route is. So all traffic that isn't part of what I would call this like an enterprise here, traffic not destined into these networks goes out to the internet via our hub here. So awesome. Let's go ahead and get started. So again, for you guys in our paid course, thank you for believing in us to get you certified. And also, all these labs are available to you, already pre-built and pre-configured. These routers are already going to have the correct IP addressing on them and a baseline, so you don't have to worry about that. The only thing you have to worry about is verifying, getting familiar with the network, and creating your static routes. For anyone watching on a free streaming service like YouTube, again, thank you, and thank you for trusting in us. Our GitLab is also, or should be posted down in the description below. CCNA video course, and this is going to be under section 5, Static Route Lab 2 Advanced. You can see here we have a network diagram, and we have our instructions here. So I'm just going to go ahead and pull those off to the side. We can also look down here for our instructions, and let's go ahead and begin this lab. So step 1, turn on all devices. So we're going to start all of our nodes. You can see here there's a lot of different nodes here, so it's going to take a while. And then step 2 is going to be paste baseline from GitLab. So again, in our paid course, people that can download this from our central repository, this is already done for you. For those of you not in our paid course, our GitLab at the root of the folder has baselines. Awesome. So now that those are all turned on, let's go ahead and console into all nodes. And there is going to be a lot of console sessions, right? And I'm using Secure CRT as my default. No. Sometimes that more actions button doesn't always work, and we got to go in one by one to click console in. And we're going to go ahead and do that. And we're going to console into everything here. Besides our switches, I mean, they're just blank, right? There is no configuration on them because we're not working with VLANs right now. So we don't need any special configuration, right? All of our devices can just go ahead and use the native VLAN for its layer 2 encapsulation. I am going to log into these servers here, just the web server, and you're going to see why when we get into the actual lab. Going to clean this up a little bit, put our routers in order. Awesome. I'm going to scroll in here, Secure CRT, so we can get a better view of all the commands I'm about to type. Awesome. And again, the instructions and the network diagram I'm using are going to be off to the right. So I'm going to be able to just quickly know where interfaces are connected to on the router. If you're wondering like, oh, how do I memorize all this? I don't. I just have a second monitor set up. Okay, so let's go through the instructions. Verify all IP addressing is correct. So let's go into R1 first. Let's verify our IP addressing. So let me just, that's a little bit clearer now. So R1, we should have ETH02 as a 7500 dot, let's see here, dot zero network. Yep. And then ETH03 should be 75.00.2. And then we have ETH10 should be 64.0.0.2. And ETH11 should be 64.0.0. Again, we just quickly look here. I labeled all of them for us. So ETH03 is 75.2, 02 is 75.0.0.0. Then I have them labeled here as well. And then this interface to the ISP is DHCP, because typically in like a small network, maybe enterprise, that's what it's going to be, right? Sometimes you can get a static IP from the ISP, and sometimes it's just not needed, okay? So with our default route here, when we make it, I'm going to go over why we want to choose to use the physical interface as the exit interface instead of the destination next top IP address. Okay, so let's go over to router 2 and verify our IP addressing here as well. Show IP interface brief. Okay, ETH10 should be .3, ETH11 should be .1, and then we have our default gateway for our LAN. Good to go there. Router 3. That's good, and then 03, yes, should be .3. And then our 4, we're going to do the exact same thing. And once we're finished, we can get into some of our configuration, right? What we're here for, static routing. All right, that is correct. And then R5 is the ISP. It should only have 2 IP addresses on it. And what I did here was literally just make a network, right? Assign this interface a network here that connects to our HQ router, and then built the DHCP pool to service any broadcasts that come across that link. And then this loopback address is just Google DNS, right? So at the end, we're going to make sure that our PCs here can ping Google, right? And that's supposed to be at the ISP level. Awesome. So step 4, from R1, configure a default route out towards the ISP. So on R1, we're going to do that. So we're going to go IP route. And then our default route is going to be 0000000. And then we're going to actually just go ahead and choose the interface here. Because technically, we wouldn't actually know the destination IP of that ISP. You know, it may rotate, or they may just not give us the information, right? We could guess, but it would just be better to point it out to something we control, which we know it's always going to be ETH00. All right, so that's step 4. Now, again, typically this is going to be on the ISP, but we also need to make sure that the ISP has a connection back to us. So we're going to go into R5 here and also just put in a default route. Now, and again, this isn't going to be typical. Typically, what would happen is the ISPs would know what IP address your Soho router or modem has, and they would just do static routes there, or you could be running a dynamic routing protocol. An ISP wouldn't have a default route out to you. But in our little sandboxed environment, that's just going to allow full reachability when we do our ping test, right? We're just mimicking what an ISP would do. If we wanted to fully make this robust, we could connect this router here to like a NAT cloud and EVNG and route it out to the actual internet via my VM's NIC. And maybe we'll do that in future labs, right? But okay, moving on, right? We're here for static labs. All right. So R1, let's just go ahead and do a ping test here. Make sure we can ping Google. All right, we have success. Obviously, that first failure there is because of ARP. We know that. Step 5, we're going to load balance traffic destined to 192.168.10.0/24 network between R3 and R4. So let's go ahead and break this down. So we're going to use static routes to load balance. So the way this works is automatically in R1, and we can look in the Ceph table as well for this, guys. So actual ingress and egress of our packets. We're going to configure two static routes from R1. One static route destined this way, one static route destined this way for this same network here, 192.168.10.0. This is going to automatically load balance for us, and this only happens on equal cost links, okay? So if this was like fast Ethernet, this was gig Ethernet, we wouldn't do this with static routes, okay? And then from R4 and R3, these guys would be considered stubs, right? Because there's no routers downstream. So, and this is typically how you want to load balance, right? You don't want to load balance if there's downstream routers because you could just get in a mess of trouble, right, with the routing and asynchronous, especially if you're using static routes. So these stub routers, R3 is going to just send a default route out to R1, and R4 is also going to send a default route out, okay? So let's go ahead and do this configuration. So it's going to be pretty simple. We're going to go into R1, and we're going to do IP route. And in this scenario for load balancing, we're actually going to choose the next hop IP address as our way to get to the 192.168 network. When you try to just use the physical interface, you actually start messing with the routing and our pings start to drop. Before I made this video, I was just running tests again, and it seems like since that's a connected network, right, and you're trying to load balance, if you use the exit interface on this static route, I think you end up having a routing loop. I'm really not too sure, but I know that it only works when I choose the next hop IP address as the destination. So that's exactly what we're going to do. So from R1, we're going to route to the 192.168.10.0 network. It's a /24. And we're going to go to the next hop IP address on R4, which is 75.0.0.1. And we'll go to the next hop IP address on R3, which is 75.0.0.3. Awesome. Now, will we be able to ping the 192.168.10 network? Okay, we are able to. So let's just go ahead and take a look at R3 and let's look at the routing table. So the reason we're able to have full reachability here, I believe, is because we're directly connected. So if we look at our routing table, just the static routes, right? That's our direct connection. So when R3 receives that ping, it's going to look at the source coming from 75.2, right? And it's going to be like, yeah, I know how to get there. So let's break this down, right? So if we were just to leave that there and we did that ping test, we would believe we have full reachability, but that's actually not true. So let's break it down, right? These ping tests we are doing, the source IP addresses are coming from these networks. And if we look at the routing tables of R3 and R4, they know how to reach these networks because they're connected, right? So the routing table, when it receives that ping or that ICMP message and has to route it back, it knows where to send it, of course. But if we sourced our pings from this interface, this routers do not know that IP address. So when it gets that return, that ICMP return message, right? Or, right, it's trying to return the ICMP or reply to that ping, it's going to look in its routing table and be like, I have no idea where 64 is. So we need to put a default route into both these routers to make sure we actually have full reachability for all of R1's networks. And just to kind of prove here, right? So if we go back to R1 and we do our ping test, ping 192.168.10.1, we're going to be like, oh, good to go. I'm a genius, right? I configured static routes. If we trace route 192.168.10.1, we see it's going to .1 there. And then, well, it will be load balancing, right? Because if we type in show IP route 192.0.0, or excuse me, 192.168.10.0, it's going to show, right, that we are load balancing here, okay? So if we try to do that ping test and we actually source it from a different network like ETH11, let me go ahead and put that source command in. It's going to be a big fat no. And the reason being is because R3 and R4's routing tables don't have the 64 network in there. So we can fix this by just doing a default route out to our upstream router. And that's totally fine because we're in a stub environment here where we don't have any downstream routing environments. So we're going to go out ETH03 here. And R4, we're going to do the same exact thing. IP route 000, our quad zeros, right? Going out ETH02. If we come back to R1, let's see if we have full reachability, and we do. So that's going to cover step 5, load balance traffic destined to the 192 network. Okay, awesome. So our next step, let me just bring something up here on the side. Our next step is going to be create a primary static route to route traffic to the 172.116.0.0/24 using ETH10 as the primary, and then create a backup secondary route using ETH11 to the same network. So let's go ahead and do that. So now we're going to create this primary and this secondary from R1. So how do we do this? So we're going to create this primary, and we're just going to do it like this. So this is the 172.16 network.0.0. It's going to be a /27. Our primary is going to be out ETH10, so ETH10. Our secondary, we're going to give an administrative distance, and we can do that with this distance command of 10. So all things equal, right? Let's go through our steps of how we pick a best route. First is the rule specificity, which are going to be equal in both these commands, right? But this AD is going to be higher. So if we look at our routing table now, we see we only have one primary way to get to that 172.16 network, and that's out ETH10. Sweet. So now let's go into R2. And how do we configure this? So R2 also being a stub network, we can just use default routes out. And then we're going to do the exact same thing, just change the administrative distance. And now, IP route static. If we go ahead into ETH1/0 and shut it down, if we type in show IP routes static, now we're going out ETH11. Pretty cool, right? So go ahead and no shut that again. That's what we call a floating static route, guys. So we've created a floating static route. So if our primary goes down, our secondary will take over. Okay, step 7. Create a host route to the web server from R1 to R2, and we're only going to use a secondary link. And this is going to be specifically for the PC7 user, a part of the 192.168.10 network. So let's go over this host route. So what we're trying to say here is that if this PC7 here wants to make a connection to this web server, we want that connection to only go over this secondary link, which isn't currently being utilized. So it's going to have dedicated bandwidth. So from R1, we're going to create that host route saying IP route to this web server via 1.1. Now, what's the problem with this? Now, there's no way for R1, at least there's no way for it in this simple static route technology for us to say, we can tell that this source IP is coming from PC7, and we're only going to send PC7 traffic down there. when we pick this host route, that rule specificity is going to come in. And in the global routing table, it's going to say, hey, if you want to reach the web server, use this. So that means all traffic hitting the web server is going to end up going over this secondary route. So really kind of, this is just a lab, right? So we're just showing you how it's possible. Now, let's say R2, we decide to say, okay, we want to send that traffic back over the secondary as well. We could do a host route to PC7. So anytime PC7 comes in, we can route it back out this secondary. But if PC8 comes in, we would either have to make another host route, make a static route for this whole subnet, or we just allow it to be rerouted out the primary. So what would happen, depending how we configure it, if we just create this host route on R1, the initial transmission is going to go out the secondary. But if we don't do any configuration change on R2, it's going to come back out ETH10. And we don't want that because that's going to be something called asynchronous routing. So really, we can't get around that with just these static routes if we just want host 7 to be able to use that. Essentially, we can make a host route back out this way for this whole network. But that means anytime these networks need to reach that web server, it's going to become asynchronous. So what we're going to do is just exactly that. We're going to, on R2, give a more specific route using the secondary to this network. And then that host route is still going to be configured on R1. So you see host route creation. And then we'll go into this PC and do a trace route. And we'll show you that. We'll show you how it's different, right? How when we trace route from the PC, it's going to use a secondary. But when we trace route from this router source from this interface here, it's going to go this way and then back out the primary. In the secondary, out the primary. So let's go ahead and do this. Okay, so from R1, we're going to create that host route. So it's going to be IP route, and then it's going to be the exact IP address. So the way we do that is by giving a /32 subnet, and then it's going to go out ETH11. That's our secondary. So now if we look at our routing table, we're going to see that specific route here. Okay, and it's going out ETH11 instead of this one, which goes out ETH10. Okay. Now, if we come to R2, show IP route, the only thing we have here is just a default static route out. So we want to say that we know PC7 is a part of that 192 network. So we're going to create a static route more specific just to that 192 network, going out our secondary. So we're going to do that. /24 going out ETH11. Show IP route static. And then boom, we see this more specific static route here. Now, if we come to PC8 and we do a trace for that 172.16.0.10, check it out. We're going to use that secondary. Now, let's say we want to trace to the other server. We use the primary because that didn't match on when we sent this trace trying to reach 172.16.0.20. That only matched this entry here, which is going out 10. But when we trace router ping for .10, that matches this entry in the routing table going out 11. So pretty cool, right? So again, when we trace this way, we're going to go out here. If we come back to R2, and if we trace route that PC, we should see the same flow, right? We're going to see going out to the secondary. And we can see that right here to the secondary. But if we, let's say, trace route to the 75.0.1, we should be using our primary, and we are. So we see how we can create a floating static route and these more specific host routes to kind of choose how we want to route, right? Administratively choose. So you guys can kind of see how with this static routing, it gets really unscalable, right? I mean, if you just take a look at this network here, it's a lot of configuration to make it do what we want. And this is why our next lecture going to OSPF is going to be good, because you're going to see how much more dynamically this is built, and you're going to see the labs be done much quicker. But again, this was good knowledge. This is going to be something that you're going to need to be tested or need to know, because you're going to be tested on it. If you look at the CCNA exam objectives, we hit them all when it comes to static routing. We know what a default route is. We know what a floating is. We know how to configure a host route. And we have a pretty good knowledge of static routes now. So I want to thank you all for viewing, and thank you, and stay tuned.